Welcome back to Math 432, Applied Combinatorics. I'm Professor Asaf. Today we're going to be discussing linear orders. So the example that we have here is, in how many ways can we arrange 3 spiders into a line? So again, when you have a combinatorial problem, one of the best approaches is just to do it. So this is one way that we could arrange them into a line. But obviously there was a choice made here, so we want to count how many different ways we could do this. So we could keep starting with red, and then I could permute the green and the blue. So this is a second way that I could align them into a row. I don't have to start with red, of course. I could start with blue. And there's another way I could start with the blue one, the blue spider, put the red spider last, and the green spider here. Now let's make sure we have enough room for all of our ways. You can already predict how many there are going to be if you didn't know the answer already, because here we started with the red spider and there were 2 ways. So starting with the blue spider, there are also 2 ways. And so starting with the green spider, we know that there are going to be 2 ways. We can have the red next or the blue next. And so our total number of ways to arrange these spiders is just 2, 4, 6. Okay? But we want to think not that the answer is 6, but the answer is sort of, how did we get there? How did we get the number 6? And in combinatorics, often the numeric answer is not really what's so interesting, but the process by which we got it. So the answer here is 6, but it's a very specific version of 6. For the first spider, we had 3 choices. So we're going to say 3 choices, and this is for the first spider. So let's suppose we chose the red guy first. Okay, well then, what do we do? Next. Now for the second spider, we can't choose the red one again, so we have a choice of 2 options. So this is the second spider. Has 2 options. He can be blue or green. Let's suppose we take the blue spider as the second option. Okay, then what's left? Well, we only have 1 spider left. So that spider has to be what we put at the end, the last spider. So this version of 6 is actually 3 times 2 times 1. And of course, we can think about it. What if we had another color of spider to choose from, right? Then we could say, well, if I've already arranged these 3 spiders into 6 possible arrangements, how can I arrange the spiders with a yellow one as well? Well, where could I put the yellow one? How many more choices do I have for the yellow spider? He could be in front of the red, between the red and the blue, between the green and the blue, or after the green. And so for 4 spiders, we get 4 times as many possibilities. So that means that we get 4 times 3 times 2 times 1, which is 24 ways to arrange 4 spiders. And then, of course, there's nothing special about the number 4 here. We can keep going, and we can generalize this to an arbitrary number of spiders. And when we do that, what we're going to get is the following theorem, which is how we enumerate linear orders. The number of ways to arrange n distinct items, distinct objects into a line is n factorial. So n factorial is a definition. It's not a formula. It's an algorithm. And it's important to point out that it is an algorithm and to get a sense of how large is n factorial, because that's going to tell you the scope of your problem. How large is n factorial? So whenever you have a problem and you come up with something that's counting something similar to linear orders, you need to know how fast does that grow. So, well, what's 0 factorial? Well, this is 1. Why? Because there's one way to do nothing. Another way to think of this is a product of n terms. So 0 factorial will be a product of 0 terms. So it's the empty product, and the empty product is going to be the multiplicative unit, which is going to be 1. Okay, 1 factorial is, of course, 1. 2 factorial is 2. 3 factorial is where it starts to get interesting. 4 factorial we just saw is 24. And then the numbers are going to continue. After 24, we get 120, 720, 5,040. 8 factorial is 40,320. 9 factorial is 362,880. And 10 factorial is 3,700,000. 628,800 and 800. So if you were going to do a problem by hand, right, where would you stop? You'd probably stop at 4 factorial. You maybe would push it to 5 factorial, depending on how dedicated you were, but you certainly wouldn't go beyond that. But once you're at 10 factorial, you're already pretty big. And I'll give you a warning, 52 factorial, which is a number that we're often going to be interested in because we'll look at different ways of doing linear orders. 52 factorial is approximately the number of atoms in the universe. So even though a computer could easily handle doing something with 10 factorial iterations, it can't handle doing 52 factorial iterations. So the size of your problem does matter. And when we're dealing with problems that involve linear orders and things that grow like n factorial, we're often going to be looking for ways to compress our data and to find more sophisticated formulas so that we can make problems tractable.